All right, 7 o'clock. Let's get started. This is one the midterm exam that you should pay attention to. It's upcoming in a month's time. I have already set the questions. There should be, you can see the page one. All right, there will be three questions, but there are parts set in the question. So, and the sitting arrangement, basically we will be using the COM1, SR1 for you guys, and SR3 for remaining of you here. Okay, so take a look. And the midterm exam, there are some of these questions that you may ask. You can find here. For those of you who have official duty, you would have to give me a letter signed by your captain and above before 21st of March for verification that you can then take the re-exam. And in case someone got fall sick on that day, you have to submit your MCs before noon to be entitled to the re-exam on the following week. Okay, so usually this is the way that we arrange the actual exam and then followed by the re-exam in a week's time. The two exams should be almost similar, but I cannot promise that this re-exam will not be as harder. Okay, usually we have to make some variation. Okay, so this is the event that you have to take note, upcoming in 4 weeks' time. For today, we are going to do the review for lecture 8. This is actually review number 7, and it's working with sequences and collections. So there's a slight difference between sequence and collections. The collections are does a bunch of things. It can be ordered or unordered. So set is included here, but not here, which is a sequence means that there is certain order, one after another. Okay. So tuple, you have the first item, which is index 0, and then the second item, index 1, and so on. Same for list. And string is treated pretty much like tuple. It's just character by character, so you can also manipulate the character by character as a sequence. For collections, we have added the dictionary and the set. Basically, the uh, dictionary, it's also okay. I should have maybe put this dictionary up here also, because dictionary is also some kind of ordered. So this is ordered. In the lecture note, it was unordered. But since 3.6 onward Python version, it is now ordered, as you will see shortly. All right, they use the different parentheses to represent. For tuple, you use a normal parenthesis. For list, you use a square bracket. And for dictionary, you curly brace. And set also curly brace. All right, so we have these are the basically the data structures. All right, so you have this as a basic data structure. As you will see from here, we actually define new type of data structures, and we call them as derived data structures. Okay, why do we work with sequence and collections? Actually, this is the most important part of the programming. You cannot run away from working with sequences for anything that is meaningful, usually. All right, because the power of computer program comes from looping. Basically, the computer can go through the loop as often as you need it. And because of the looping, you will have to deal with lots of data. And dealing with data in traditionally, this is called array. And in this Python, it is either tuple, list, dictionary, or set, or even sometimes you deal with string as well, and so on. So the power of a program, it's coming from this because you can write something only a few lines, and this thing can be executed over and over again. And of course, if you're just doing some calculations without storing the value, it's of less meaningful. So usually, the loop come with a handling of data, and the data are called the arrays. Okay, and the arrays, as such, you have to have a way to refer to all those variables. So traditionally, as you and before you know about array, you may be using variable name one after another. That it's kind of tedious. All right, you always have to create new names. With the use of all these sequence or collections, actually you can refer to the particular guy with the index. Okay, so the power come with varying the index of an array that allows you to then play with putting things here and there and so on, and without having to create new names for all these with the same name with a different index to means various different variables that you can work with. So the typical type of things that you deal with in array is searching, sorting, mapping, filtering, and aggregating. So I mentioned this before. Actually, this it's also the way that when you see big data, like data that you see from Google, when you go to Google, you actually do some searching. Actually, before you can search things, actually things may have been sorted, and then things may have been mapped to some calculations, or things have been filtered away, or things that have been summarized in some sense. So all these are big data that come in array, and array has index that allows you to refer to them. So this is why we have array. It's a very important part of the whole picture. Purely with a loop, it may not be as complete. So you must have the loop that work with array to then be able to change things that are needed in the computation. All right. So which sequence? Then the question is that uh, when you have all these different types of things, they look similar, and yet they are all different. And how do you know which one to use? Here, it's the question that we actually addressed last week also. We deal with things that we wanted to know their similarity, their differences, and we want to know what are the options available to us. All right, so this is the question that we naturally have to ask about sequence or collections. Okay. All right. Then the decisions to go with which particular types of data structure. So these are all the different data structures. It's come from I would call it the word with frequency of each type of operation. You have the data. The kind of operation you deal with are searching, sorting, mapping, filtering, aggregating. And before you can do searching, sorting, mapping, filtering, aggregating, you are actually doing sometime updating. All right to the data. You sometimes delete the thing. Of course, you must have added it beforehand, or must have do some calculation, which is the form of mapping. All right. So all these are the kind of things that we deal with the data. So when I talk about frequency, it's we're looking at all these operations, which one are more commonly being used, or which one are more happening more often, and you will want to bias, you want to skew your representation to support those that you are dealing with most often or most important. Okay, like if you do a lot of adding and deletion, so you will want that the data structure that you choose is easy to do addition and deletion. In this case, tuple is not suitable anymore because tuple, whenever you do addition and deletion, you are actually destroying the existing tuple and creating a new tuple. All right, so this is how you would judge your decision on which of the data type. Then you would ask what is the use of tuple? Actually, tuple has its use also. It is useful for as a key for dictionary. While the case of list cannot be used as a key for dictionary. All right. So everything that you create or everything that we see must have it has a use of it. This is there's a Chinese saying that those of you who study Chinese will know. All right. They whenever something is there, like ourselves, we are there because of our purpose. Okay. So it's the same for data structure. They are created not equally, but they are created for purpose. Okay. So just like us. All right. So the data but one thing to note is that frequency is hard to come by, meaning that you have to put the thing into operation before you can see how people use it. So you can't tell beforehand that what is going to be more important. All right. So, but this kind of thing is then become a guesstimation, or you guess it, or you sense something about how people may use it, or you can do some simulations of things to work on the data and then judge from there which are the kind of thing that more often they're happening. Of course, this cannot be foolproof because all these are guesswork. And actually, computer science allowed you to build data structure as a data as an abstraction, just like function as an abstraction. You saw in picture language, right? You do not know how the things are implemented. For example, you want to show some rune. You don't know how it's actually being implemented, but you don't care because you don't have to care about it. You just know how it is being used and you just use it without knowing. This is how computer science or the software layers after layers. So you're dealing with certain layers and you work on that layer without having to know anything below it. All right, as long as you follow the protocol, the way that you handshake things, then you will be able to use it correctly. And so in data structures, the same thing as you will see in lecture 10, on the complex number. There are a few representation of complex number. Okay, and you can see that actually you can swap from the use of one to the other without any paying anything because whoever uses the complex number doesn't know how complex number is implemented. So by swapping the implementation, it doesn't hurt whoever is using the complex number. But what the person that uses the complex number may gain is that you may actually swap from one less efficient data structure to another one which is more efficient. Because at that time, before the swap, maybe you have collected enough statistics about how things are being used, and from there you can then deduce which is a better way to create your data structure. And that change doesn't affect anything above that layer because of data abstraction. So you will learn about data abstraction, meaning that you only know this data can support all these various kinds of operations. As to how they are supported physically or in the real life, you don't care. You just know that it's being supported. That's all. Okay, so you take a look at lecture 10. Subsequently, this is lecture 8. Lecture 10 is upcoming. You will know that you can actually swap things around without having to pay for redeveloping. As you can see, like very often, for example, somebody asked me how the Python version that's so you have Python 3.12. So now we are Python 3. We are using Python 3.11. So there are changes in there. The changes actually helps to sometimes fix bugs, sometimes improve the efficiency. All right, and if there is another great improvement or great development, the Python may become 4.0. Okay, and that can then that time, then some of these backward compatibility may not be there anymore, and some of the thing that you write may not be transferable from version 3 to version 4, and some these maybe require some work, and because it's a certain change in the data abstraction. Okay, so anyhow, the data abstraction it's an interesting thing that in computer science we always build things from layer by layer, and we hardly needed to touch any layer below the one that we are working with. All right. So, but there's a caveat here in our assessment, okay, meaning that in the way that we structure our question, for example, in midterm, I have already set out the questions. I may have to force you to use certain data structure, okay, but that doesn't mean that data structure suit the purpose the best, but it just suit our questions to test you on certain concepts. Okay, so for assessment, we have to force you to do particular data structure. You don't question us. You just have to use them as what we stated. All right. All right. As I said just now, each one has its own purpose. So tuple is there. Existence of tuple. It's for possibly as a key to dictionary, other than many other things also. List, existence of list is to ease in the way that you are needed to update the array. Traditionally, our array in other languages, they are actually more like a list. I didn't know about tuple until I learned about Python. All right, so most likely those of you who know traditional languages, array usually refer to list. Okay, so we know that each one has its own purpose. Then we needed to know, like last week, how each one is the difference, the similarity, and the options available to us. All right. So as we just saw, tuple is immutable, as list is mutable. So this is one characteristics that you should take note. And you know that tuple, list, and dictionary are ordered. Okay, so maybe I change this to ordered. And after 3.6, so this is after version Python 3.6, this is actually ordered. And there are things that these are so-called primitive, and you can have derived. Just like what you did in picture language, we have some of these primitive to show this, to turn 90 degree, and so on. You can then combine them to turn 180 degree or 270 degree or even one round. Okay, so means a combination allows you to do that, to put a few of them together and to do even more other functionality. Or you can also have making it into a function. Okay, so it's similar for data structure. We can do the primitive as a type given to you, and derive primitive like the tuple, the list, the dictionary. Whereas derive maybe like all right, like priority queue, AVL tree, red tree, red black tree, 233, and so on. All these are the derived. They are not the native, but you can combine things together into priority queue, AVL tree, and so on. These are all some terminology you can just Google and see. These are different types of tree, but all in all, while the existence of all these is with one main purpose, that is the balance. All right, whenever we do things, we always want balance. You want to balance your work with life. You want to balance, in this case, the depth with the width. You don't want the depth to be too deep, while the thing is so narrow in the tree. You want it to be pretty bushy, and so that you can have a shorter tree. Okay. And so these are all the existence of all these things are different form of balance. All right. Then in last week, we also saw that we have to know how to deal with each of these types of things. And we have to know how to work with each of them, how to work with tuple, how to work with list, how to work with dictionary, how to work with set. After knowing that, you need to know how to pass the information of tuple, list, dictionary, set into a function. And having done that, you also need to know how to do with recursive call, because recursion it's the thing that costing a lot of the data usage, and because you're creating new things and so on. So these are the 3 points that usually in understanding a particular thing, you yourself should try things out. And for today, I'm going to try it out for you here. So I have created this. I will post this into the as a code in later on after I'm done with these lessons. So basically, I've created all of them here: tuple, list, set, dictionary. All right. So let's see. So this is for tuple. All right. You have a tuple of this. I print out the tuple with ID T means the address. We saw this thing last week. All right, so this is the address. It's a long string. It's an integer number that is representing the location. So for I in T, print I. This is to show you that the if you have 1, 2, 3, 4, 5, it will come out as 1, 2, 3, 4, 5 as a sequence as ordered. All right. Then now you have another tuple S, right? The meaning that the T and the S are now pointing to the same tuple. Now, if I change T with added with a 6 at the back, you can see that actually this is being destroyed from T, and T is here. And this one's still here because S is still using it. On the other hand, if you don't have the S there, all right, and then you will see that as if, okay, now here, right, as if that there's something added. But if you check the ID, right, the ID was printed here. The ID was this, the location. If you check it, you see that this is actually different from this, which means that the original one was destroyed because it was a garbage with nobody pointing to it. And this is a new one that created at this new location. So that is to say that from the old 1, 2, 3, 4, 5, you get to 1, 2, 3, 4, 5, 6, you are actually creating a new tuple. You pay the price of all the number copying. That's why we have to pay, in this case, the complexity of this operation is not constant, but it's actually this is O of n, where n is the length of new t. Okay. All right. So this is how the tuple it's like. Even though you put plus equal to this, this is no difference from equal to, if you put t plus this, you're going to get the same thing. Let me put back this s. Okay, here. And then you have the s is equal to t, both of them. Now I have a t is equal to the t plus this guy. You see that I'm pretty much copying down all the things and added a 6 at the back. So I'm paying for every single entries here with time on, where n is the length. You see that the address here is different from here. Okay. Of course, you compare the whole string, whole address. Oh yeah, just highlight the part that is different. Okay, these are different. These last 6 characters are different. Okay, now we see list. List is mutable, so you can actually change the list directly. So you have this list 1, 2, 3, 4, 5. Then you print. You should see 1, 2, 3, 4, 5. Okay, all right. Now, if you append 6, the 6 will be here. All right, now we check the address. The address was this, printed out. It was printed out here. Now, you see that this address, no change. It's the same thing. Okay. So this is what the list allowed you to do. So this list, on the other hand, if you try a different one, you will put this looks like what we did here. And let me just comment out this. Okay. And let's see what happened. Are they the same? We're here. Okay. And now we do this. So the list plus 6. So this is the list. We still have the 6 at the back, but now we can't be sure, right? The picture can be deceiving. We have to see what happened to the address. Is this the same location? So the location was 161,352. Actually, it's different. You see, 6161,352 now it's 313,288. So this is indeed actually a new one. All right, we can also verify that by doing the same as here. We can use S is equal to LST just to keep track of it. Okay, here. All right, we have this two guy. Now we add this. You see that it's split off, so the S remains here. So this is a new guy. Okay. Now, well, one more that I didn't try yesterday. So this is one. If I do this, all right, just now when I did it for the tuple, no difference. But here, let's see. I'm here. My S and my list are pointing to here. Now I add this. Oh, now no change. Okay, even though they looks the same, and yet so this guy is different from LST equal to LST plus 6, which created a new list. Okay. So this is annoying in some way, annoying because this is actually this looks like a shorthand for this guy, but in fact this and this are different. So and somehow the interpreter for Python, or I should have changed it to 11. Let's try the 11. It should be the same in this case. Yeah. Yeah, it's the same. So it's annoying because to us this as if to be this, but somehow the interpreter can interpret this in the intention of list dot append 6. But the interpreter cannot interpret this because this happened to be the same as this guy, but still play safe. This it doesn't want to assume that, and therefore this is creating a new list. All right, so this is a little bit counterintuitive. This looks like this, but yet they are different. For such a case, there could be a number of such things in Python. It doesn't make much sense to test you on this kind of stuff. I mean, in the assessment, we will avoid having to test you on this kind of technicality that it's pretty much implementation dependent. That is to say that the interpreter know how to interpret this guy as append 6, but he doesn't know how to interpret this guy as append 6. So this is a little bit not fair to you that I would I found it out because I tried. But this kind of thing, by studying, you can't tell. You only by experiencing. Of course, you should not. You should do a lot of experimentation yourself to get used to some of this stuff. But still, all in all, this is still very much implementation dependent that I would want to avoid having to test you on this. Okay, so just to reassure you that we don't do such kind of stuff, but you remember that it can happen. Okay, now we look at sets. Set is supposed to be unordered. So what does it mean by unordered? Look, so you are now creating a set. Now you see a bunch of things in the back. Okay, here's a bunch of things in the back. You don't know who comes first. It could be clockwise, counterclockwise, or whatever order. It can zigzag also. Okay, but let's see. So we first of all print out the location of these sets. Next, we see one by one. So you can't tell which one is going to come out first. You put it in as A, B, A, C, and D. So let's see. It come out at D first. I mean the last one come first. Then it come with AC, the second last one. A. Oh, you thought that it's going to come from the back, but now it jumped to the front. So there is no particular order. All right. So you had D, A, C, A, B. Okay. So don't back on. So you cannot back on any of these order for your processing. You have to your processing should not depend on this kind of stuff on the order. All right. Set has no order. Okay. Now we add another guy DD into this bag and see what happens. The DD is added. So we want to check whether the location has changed. So we had the location like this. Now we see the location is still the same. Okay. No change to the location. It's just simply added another guy into the sets. Okay. Now let's print out the order. Just now we had the order D, A, C, A, A, B. So what happened now? And now is A come out first. A is the first guy. AB, it looks like the second guy. Now it seems to respect what we put in. AC come out. And D come out. And it seems to respect it, but you can be assured that from this earlier printout is not in any order. Okay, so don't back on any order about sets. Last but not the least, it's dictionary. Dictionary, I didn't actually the, emphasize that, but this is the index that make a difference uh, for 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 dictionary versus tuple list and string and also sets. Okay, those indexes are all in 0, 1, 2, 3, 4, 5 in some sequence. But dictionary is not. You see, dictionary is ordered, but then the so-called index is not necessarily number. These are the so-called index or the key. So the key 44 has the value 1. The key 11 has the value 2. The key 299 has the value 3. The key 3 has a 4. Okay, let's see. All right, it's like this. All right, so it's actually not like the set case. It printed out in the order. It doesn't list it in this manner, but it lists it out in this. It makes sense because dictionary after 3.6 it's an order. It's an order sequence. So 44 is the first number to go in. 11 is the next number or next key. 299 is the next one, and 3 is the last one. Okay, so you have this listed out in the order. So when you print it out, you should expect to get the order. Okay, so this is the original location. Now we see what come up. For I index is just to print out the key. So the key is 44. Next 11. Next is 299. Next is 3. All right, in the order that we see. And the value wise, the values are on the right column. This is the left column. This is the right. So this is a key with this value. This is a key with this value, and so on. So the 1, 2, 3, 4. Okay. Now, so we can now add something, or maybe we can make it even more bizarre a little bit. Let me change this. Instead of this, we can put it as a string A, B, C. It's a number and a string. Okay. All right, so we are here. We want to see how does it look like, any change. So as this syntax is to say that adding this new key, this new index with these values. All right, so this index will be put down here. Then the value will be the next one. Okay, you see. All right, so it's still in order. So if you check the dictionary, the location remains the same. right? It was 4576, it's still 4576. Okay, now the number are still in the order, no change. And the value also in the order, no change. Okay. Now if you want, oh here. Now this is to pop up 299. 299 is here, pop it out is to get the value 3 and print it out. And this is pop means that you get rid of it. All right. And then you then you print the ID. You want to check what is the ID. Is it still the same location, 4576? Indeed, it's still the same place. So there's no change to that. All right. And then the value is still 1, 2, 3, 4, 8, and so on. Okay. So these are the things that what I'm trying, and you should be doing your part to try out yourself. Okay. We're here. Okay, great. All right. So we did talk about these things that if you these are the things that you have to know. Of course, it's an open book exam and midterm. You can always refer to all these guys that they are, what do they mean, and so on. As I mentioned last week. Okay. Now this lecture is about example of tree. Tree is not anymore linear. It's you see the lecture, the tree, all right, the tree is a tuple of tuples or sequence of sequences. All right, and it looks like more bizarre. All right, it has all much more not no longer one straight line, but as I say, we always want this kind of tree. We don't want one straight line. And one straight line is simply like a tuple or a list that we already have. The purpose of a tree is to make it into all this kind of structure to shorten the height. All right. So now here, for example, you have 2, 4, 6, 8, 9 items. These are called the leaves, and you have 9 items, but the height is only 1, 2, or 1, 2, 3. 1, 2. Okay. So instead of putting it into straight line, this allow us to quickly retrieve information from the leaf of the tree quickly because it's shorter in height. That's the purpose of tree. So you can see that tree itself is already not a primitive data type because we're using tuple of tuples. All right, so tuple of tuple is a derived type already. So in a derived data type, actually it means that you don't have like in the case of function, we give you this function, but you can, for turning 90 degree, you can make turning 2 times 90 degree to turn 180 degree. Same here. So this one is we give you tuple, you can create tuple of tuples. All right, so this become a derived data type. So this kind of derived data type is needed for its purpose. So as you can see, in very often in the databases, you will see that they will be the red black tree or the 2-tree tree. All this kind of stuff appear in all the advanced courses. All right, so these are the 3 columns that usually you should know. The column about primitive data type, which are the tuple, list, dictionary, and set. Okay, and set. Okay, and the column about derived data type, it's needed because of applications. All right, so some application will require you to combine some of these data types into a data type that are useful for the application. So the application dictates the type of things that you should create in a way that you can do mix and match so that you have something interesting that will serve the purpose we talk about, that about the frequency, that you know which are the kind of stuff that you want to do most and how should you capitalize on that to make sure that your application then can benefit from that particular data structures. All right. So for example, in the case of databases, I told you just now, you got no choice but to use this kind of 2-tree tree or red black tree or AVL tree. Okay, AVL3 is the name after the inventor, the 3%. All right. So let's see. In here, I posted also in the forum about this slide 51. All right, so this code is kind of amazing. It's such a short code, but it does be able to take every value here and multiply with some number to give you the scaling, the factor. This code, you should try to see how you can write this code in an iterative manner. But of course, the iterative manner must also embed with recursive. So I did post it just now. Yeah, yeah. All right, this is my question. How do you do? Oh, yeah, question to you. How can you do iterative version of it with a for loop, but there's some form of recursion within the for loop, but without using the map. Okay, so this is an interesting question. Okay, and let's see. So let me just run through this thing. Before that, there are two links here about the time complexity. At time we have to refer to them because the I posted this last week about min and max. In this case, you see that min and max actually is O of n for the list, for doing list to find the min and max. Basically, you can guess that this is to go through all the items in the list to find out the minimum or the maximum. All right, so of course it's this. And then why is this a O of 1 get length? Don't you have to go through all the items in the list to be able to tell the length? Yes, that's true. But you may be able to do some magic by whenever you do deletion, whenever you do addition, insertion, then you go and update the length. So the length is now not a part of the data, but it's a metadata. All right, then you will be able to achieve O of 1. So in this case, this is how list is implemented in Python. So you have to accept that this is O of 1. All right, even though we know that to get the length, you actually, by right, you should go through every items to see that and then to count it as to count it into the total count. But because of special things that we built into the data structure, we can take it as what is given here. So this is the web page about Python, but this page, it's stated there that is no longer be maintained. It may be disappearing soon. So this is the other one. These are the pythoncomplexity.com. You can refer to this page also. This page is it's more click needed to get from one place to another. So this one is only on the list. If you want to know about the tuple, you have to go to the tuple link and so on. All right. So anyway, this one will be there. This will not only be there for a long time. This one will be there at least. This is what this guy referred to that I should go to. Okay, so at time you have to refer to this for the complexity. But when you see it, you should be able to tell why certain thing is like that with your current knowledge. Now, for tuple, I just want to run through quickly that it is the searching of the thing is O of n with the item in the tuple. Adding is O of n. Let's see, is it O of n tuple? Oh, it's not here. Tuple is here. Uh, okay, maybe I don't know how to find it. Anyhow, so the adding is O of n because you know this tuple is immutable, and so you have to destroy the old one and create a new one. Modifying is the same thing. You have to destroy the old one and you to make a new one, even though you're just doing a simple modification. But why it's there, it can be used for hashing. Alright, whereas list cannot be used for hashing. Okay, list means this one. So tuple is also a linear structure. Okay. And what about list? List, it's a searching is O of n. Just in case you're unlucky, we have to search for something which is in the middle. Right. Adding it's if you are unlucky, you're adding in somewhere in the middle or somewhere in the front. You cannot just simply append. So you have to pay for O of half n, which is O of n. All right, let's see. All right, append it's O of 1, that is the last one. Then uh you are insert. What is insertion? Okay, this one need to study a little bit. The why is some of the stuff are like that. All right, you're adding to the front, you are in trouble because you have to shift all the thing to the back by one. Of course, there's a derived data structure that you can build with this double linked list, and you can then achieve this with O of 1 also. Okay, but we'll see. It's in the other class. Modification, you can directly modify if you know the positions. And the length of the list is O of 1. Why? Because it's implementation, get length is O of 1. Yes. Min-max problem with deleting of min-max. So min-max is O of n, meaning that it doesn't actually have this metadata. But this guy does it say about it? Okay, it doesn't. Okay. So this is some of the things that you should remember. Okay, you got no choice but to memorize them by heart in a way. But as you use them, you will get used to it, right? So dictionary, it's not available in some other languages. Most of the languages that I know did not or do not have it. This is I encountered this thing in Python. Searching is O of 1 because of hashing. Actually, this is a trade-off of time and space. Actually, in dictionary, you just now when you saw the picture, you saw it looks like this, right? As if that there are only four locations, but in fact, dictionary needs a big space. And this four location is just simply collected together and put in here. In actual fact, they are all scattered in the storage so that it can be retrieved in constant time, and hopefully there's no collision. So this is like in real life that you have a big bookshelf, you know where the bookshelf, it's you have more than enough space, so you can put your computer science book in one place, book your mathematics books in another place, so that whenever you say I want mathematics, you know where to get it very quickly without having to check one by one. You don't have to even touch the computer science books. You can just simply go to the place where you have the math. So the the assumption here is that you have big enough space. All right. So to be able to allow you to do this kind of hashing. Okay, hashing is something. All right, adding is O of 1 in the good case, but it's a bad case is O of n. All right, things like this. I have something here. Oh, Python 3.6 dictionary is ordered. All right. So, but there's one tricky thing about listing out item in the dictionary. Somehow, just now we managed to get the listing out 44, 11, 3, and this guy in the order like as if nothing happened. But actually, underlying, you need some kind of linking of one item to the next. And this kind of linking actually preserve the order that you added it in. But on the other hand, it also is a pain because you have to maintain this link. When you delete something, you have to relink things around and so on. All right. All right. Here it's stated that as I say, the requirement is that you don't see actually four only, but you have a big space to be able to a big bookshelf or something that you can keep just a few books. Right, it's the same idea. And when you have collected more and more books, you got no choice but to buy bigger and bigger bookshelf with more slots available for you to play with compartmentalizing your bookshelves. Okay. And set it's an interesting thing. It doesn't have any order. It just on the other hand, it has this thing the called the union find. It's a very powerful data structure to support membership. Right, and this is come from application. In the era of compiler development, people needed to tell, oh, this variable it's already defined or not yet defined. They use this kind of set union find to achieve that kind of constant time complexity. Okay, so this column is primitive. This is a derived data type. The complex number, as you will see in lecture 10. And also you see along the way, the queue, the stack, all these are also kind of derived data structure. Basically, with the original data structure, you add on something or you put in metadata, or it's also a derived data structure. You can also combine the tuple and list together. For example, when your application requires you to, at time to be able to do updating fast, and at time you want to be able to index your dictionary at the same time. So you would have to have a mixture of this tuple and list in the same application. Just one note here that afterward, when we look at recitation number 4, the use of the tuple is kind of like unreasonable because it costs a lot of time and space. But anyhow, we just do it as what we are told, like what I told you that in our assessment, whenever we tell you to use that thing, don't run away with it. But you can always question it by doing it another way. Besides fulfilling the requirement, you can also try the question with other way of solving it and to practice your skill. Okay, I think I'm pretty much done here. Let me just summarize this. Okay, you of course the first thing is that you have before you use it, you must understand them. Actually, you must understand them in these following 3 ways. All right, must understand them how to work with it. You must understand them how to pass to function. You must understand them what is the implication in recursion. We'll see that in recitation afterward. All right, there are possibility of derived type, and these are common. Um, these are usually the way that we can play with questions and to test you. Okay, one more thing that I should say, which I did in yesterday's session, it's that by now you know how to write code anyhow in some way. All right, not anyhow to the extreme lah, huh? But anyhow you just hope your first goal is to get it correct. Then after you know how to write code, you want to write good code. Okay, meaning you make commands, you make meaningful variables. After you have the good codes, you have command and so on. But the thing may not run as what you wanted, so we study time and space complexity. So from anyhow code, we get to good code, and then we get to efficient code. Okay, and one important part is that you want to get to correct code. All right, this is the most difficult one. It's most difficult because computer science is very much close to mathematics. Whatever you write here, like these are sequence or nothing. As I mentioned just now, any meaningful application, you cannot run away with looping. Okay, you cannot run away from looping. You surely have some form of looping, and because of looping, and you would have to have ways to talk about why certain thing you do it's correct, right? And that is a proof. And this kind of proof has mathematics as the foundation. And I will show you a little bit next week in our review. But for now, just bear in mind that correctness it's very interesting, and also, of course, it's not an easy topic that we should delve too much with. We'll deal with it a little bit, but not so much. All right. So proof of this is not in this course, but we will give you some hints about this thing. Even if we ask you to do a little bit, there are some basic logic that you should know. All right. So I talked so much, everything. Any question? You okay? Give me a check. You okay? Okay. Today we don't have many students. Oh, interesting. We have only 16 of you, or 15. All right. And let's take a short break. We continue at in 5 minutes time. All right, 8 o'clock. Let's get started. So you should uh, now know that the midterm exam is upcoming in a month's time on a Saturday. Here are all the details that if you have official duty, you have to submit by 21st of March, and we'll get you a re-exam. The re-exam is always a week after the actual exam, so or the test. And this is the date for the re, but the actual one is on the 28th of March. Should uh, 146 on that day, unfortunately, then you have to the one has to submit the MCs before noon to and re-exam will also be arranged. Okay, and then today we are talking about recitation number 4. It's on data abstraction. So this is pretty much lecture 7 and lecture 8. Then here in this particular recitation, it focuses on the tuple. And in actual fact, you could have done this whole exercise applying it to list, for example. Right? Dictionary may not be so appropriate, but list should well be appropriate. The difference is that the list is now mutable and some of the stuff could be done more efficiently. Okay, we shall see. All right, so tuple is a collection of things that it has one after another, the value, it's immutable. And you can use operation. These are called the methods. The length to find out the length and the number of elements in there. Elements in this is for iteration, or you check whether it's there or for something in there or not. Maximum and minimum. Okay, so let's take a look. Uh, all right, so here is a list. I did this thing just now in some way, but let's quickly, a few of you just join us. So let's get through this quickly. All right, so this is a tuple. This tuple has the length of 1, 2, 3, 4. All right. So this is a tuple of tuple. So this is the tuple inside here. This is actually another tuple, but this is counted as one. So 1, 2, 3, 4. All right. Even though there are 1, 2, 3, 4, 5 elements in total, but there are actually four for this T length 4. Okay. If you have S and T, then both of them are pointed to. And so this is I did this thing pretty much. So the address of S, this is the address of S and the address of T are the identical. That's true. What is the address of S? that it's this. The t is equal to t plus 4. This is actually making a new t. So even though the two guys are there, now if you have it, so this guy is a new one, the old one remains there. But these two pointers are copied verbatimly into the other guy, and the 4 is added here. So the address of t now is no longer the same as the address of s. This is different from this. Okay, and ID of the second item, ID of the second item is this guy. All right, and ID of the S second item is this guy. Both of them are actually the same. All right, they are still true. And the S, it's this whole thing, and its ID is this. T is the whole thing. The ID is this, and the ID of S and ID of T no longer the same. Just now we saw. And now, in terms of list, so this is the list. This list is 1, 2, 3, another guy, and then a 4. So this is 1, 2, 3, 4, 5. Actually, 5 elements. M equal to K. All right, M equal to K. Then both of them are pointing to here. K dot append 5. So K is appended with a 5. And you see that the M is also got affected. This is a side effect for M, which usually we don't like. To change something, but yet another thing got affected. And this is, at times it can be annoying for debugging, but we don't like this kind of thing. Two things pointing the same, and yet one thing got changed, the other one got changed. The ID of M and the T are still, M and K are still the same. All right, so ID of M before adding 4, which I'm going to add 4. All right, before adding 4 is this guy. So both of them are the same. So M plus 4. Now I'm changing the list. Now you see that this M no longer the old M, but the new M with a 4 at the back. All right, so this it's different from the in place append. All right, so this is ID of M is no longer the same. Okay. All right, but on the other hand, if you put K plus equal to 4, this guy with the 4 at the back, you are actually the ID now before it's here. Now, if you do this, you actually no change to the address, you see. Right, so you see this still the same. So basically what I meant is that instead of using, okay, let's do it. If this is changed to plus, okay, then they will be the same. Here, like here. So just now these two, right? When I did just now the one, you will boom, another new guy come up. But now it doesn't. So it's the same. So it's what this is trying to illustrate. Okay. Now this one should be the same. Okay. Whereas just now if I had done this thing with a M plus the ID of M and K, they are not the same. Okay. ID of 3, M3, which is this guy and this guy, they are actually the same. But even though the parent is not the same, but these two are the child, they are the same. And that's it for this guy. Okay, so let's do this one is another one that I should demonstrate to you. Okay, this one it's I'm trying to illustrate 3.6 versus 3.11. They are different. Okay, so let's see. This is 3.6 at the moment. Okay, let's go through. This is I told you just now, besides knowing how to work with the tuple itself, you also must know how tuple pass to function is being used. Right, so here it is. So T is this guy. So we have this guy. we pass the t into the function foo, right? And now t is equal to this guy. Okay, so basically this t and this t are the same. Okay, and created this when you assign it, you now get a new guy. You basically get a new copy. All right, when you return, of course, this guy you return nothing. This is destroyed. Okay, all right. So now if we change this to 11. All right, now this T, both of them are pointing here. Just now with this execution of this line, this T pointed to a new guy. Let's see now. It doesn't. Okay. So the version 11 and the version 6 are quite kind of different. These minor differences. All right, so it does it. On the other hand, if you have different values, in this case the different value, both version is going to give you the same thing. All right, yeah, for version 11 and for version 6, they are going to be creating this guy. So this minor difference between the two versions is something which is implementation dependent. So we should not be testing you on this kind of stuff in your assessment. All right, there are 4 questions. So let's get through this 4 question. Okay, now you can help me. Is that Ton Liao?
Hello, can you hear me, Prof?
Yeah. Okay, let's
Yeah.
try. Okay. Oh, okay. Tuple is this. This is question number 1.
Yep.
What do I have? What do we print out? Print tuple A.
It's just a tuple with the 4 elements, 10, 12, 13, and 14.
Okay. Next, tuple B is this. Print
Uh,
tuple.
yeah, it's just the 2 elements.
Okay. Then this one.
Tuple C, it will concatenate the 2 tuples to create a tuple with 6 elements with 10,
Hmm.
12, 13, 14, and the other 2. Yeah.
Yeah, you see that they are created taking this and then copy down, taking this, copy at the back.
Yep.
Okay. And 14 in tuple A.
14 in tuple is true because it's an element
True.
of the tuple.
Yeah, in means true or false. Okay, true. 11 in tuple C.
Is false because it's not an element inside the tuple.
Okay. Tuple D equal to tuple B 0 times 4.
Will be this, uh you will print out 4 of the CS1010X string in the tuple.
String. String or tuple?
The element is a string, but it's
Yeah.
uh in a tuple.
Oh, then you're wrong.
Oh,
It's a string.
O is a concatenator. Oh,
Yeah.
okay.
It's item. Take out the string 4 times. So one thing you have to note is that tuple and string behave pretty much the same. But once you take it out as a string already, you have to work at it as a string. So the string is copy 4 times. 1, 2, 3, and 4 times. Okay. Next, tuple D 0.
Uh, it's just the CS1010X string because it's calling the element.
0, 0.
CS1010 0.
This is a string. A string
Oh,
that,
so uh oh, so I have to look at the whole string and see the first elements, which is just C, is it?
yes.
Okay.
Next.
Uh, One is the long string, but excluding the letter C,
Okay.
the first letter C. Yeah.
Yeah. Count. So
Count
what will be the count?
tuple A. You add everything to give a sum of 49.
Okay.
Yeah. Uh,
49. Maximum tuple A.
the largest element, which is 14.
Minimum.
The least element, which is 10.
Maximum.
Tuple C. Uh, I think there will be an error because there's both integers and strings.
Yeah. You cannot compare integer with string uh, but in the way that Python operates. In other languages, it may be possible. So, yes, you're right. In this case is error. Okay.
Okay.
Uh, Not supported between instance of string and integer. Okay. So the next one also not allowed because it's minimum of tuple C. Okay. So this is question number one. Question number two. Oh, here I have another one. Question number one. Just let's do this. My example. Okay, let's try. Yi Chen Yang Yi Chen.
可以啊。
Hi. Okay, let's try this. Temp C is this. So I have this. Print maximum temp C.
Is it capital AA?
Why?
Cause there's the order, the list of order.
Yeah, you're right. So we check the ASCII code. Capital A it's 65. Capital lower A it's 97. So we will want a maximum. Oh, you're wrong, huh?
Oh,
Capital A
wrong.
is uh capital A is smaller than lowercase a, right?
Oh, yeah.
Let's try capital lowercase b it's 98. Capital B it's 66. So the lowercase it's behind, capital case is in front. So the maximum will be lowercase. Okay, so among the lower cases, you have this one, this one, this one, this one. Ignore these two. So which one is bigger?
So you compare the first one, right?
Correct.
So
This is the dictionary
yeah,
order.
so B is the larger one.
Yeah,
Then
B is
you
larger.
compare the second alphabet, right?
Yeah, then who is
Then so
larger?
what? So is index two.
Index 2. Okay, it's PABB. Okay, what about minimum?
Index four.
You mean AA? Because ordinary number of A is 65, B is 66, so this is correct. It's capital A. All right, so next, C plus AB.
Just concatenate both tuple. So 1, 2, 4, 5 A, B, C.
Okay, 1, 2, 4, 5, A, B, C. Next, D equal to A times 3.
So is 1, 2, 4, 5, 1, 2, 4, 5, and 1, 2, 4, 5.
Okay, 4 on the board. Okay, next, D equal to A times 3.
Is it the same thing?
Yeah, it's the same thing. This parenthesis is useless.
Uh,
Always remember that if you want it to be meaningful, it has to be a comma there. Okay, so this is the same as this guy. Okay, so no change to this guy. Is that what you mean?
yeah.
No change. Yes. What about the address?
I think the same.
No, no, no. This is tuple. Okay, this is before, huh? Let's see. After, they're different.
Oh,
Basically, the old one has been destroyed and the new one is created. Right? Tuple. Even though the same, but you see, it's destroyed. Okay, if you want to check that, it's easy. We can do this. Uh, okay, then you will see that right here we have a FFF pointing to the same. Now we do this. You see, you have created a new one. Okay.
yeah.
Okay. Next, E equal to this times 3. A is
Uh,
here.
is it like a tuple is a tuple? So, 1, 2, 4, 5, then the whole thing bracket. No, no, no.
You're right. Yes, you're right.
Sorry.
Yeah. E is a tuple of tuple, and the three of them are here. All right.
Alright.
Okay. So A is equal to 1, 2. So now I want to change this tuple to 1, 2. What happened to E?
Point to a new tuple.
Huh?
Is it?
No. No.
Because you changed the A. So A now points to a new tuple. Like,
Yes. And these three guys cannot touch. They are still here. Okay, let's see. See? Oh, sorry. Okay, we're here. So now this guy will be destroyed. But this guy was already pointed to by these three guys. So they cannot be touched. And a new guy come out. Okay?
yeah,
Chen. Okay, next. Print E. To verify that E, you will see three tuples still the same. Length of A. Length of A it's now 2 only, right?
yeah,
Length of D. Length of D is this guy times this, which is the this long thing. 12. Length of E is still 3. Okay? Okay, next, Chen. 1 in A,
true,
true. A in A,
false,
false. A in A,
true,
no, no, no. Yeah, this is the basic thing in the set. A in A is not true. But A in this one, these are the same thing, so again not true. A in this then is true. But this is the set theory that you learn in high school. This is a collection of thing. Is this thing inside the collection of thing? What you're seeing is yes. This is a collection of this is itself is a collection. Alright. A is not in itself. Okay, it's only this case that A is in a collection. Therefore, A is in there. Is that okay for you now?
yeah,
Okay, next. A in here.
no, false.
Huh?
Is it false?
What?
Because the location is different, right?
Yeah, but this does it talk about location? In. Return true. Oh, this is a if. This is spelled wrongly. if element is in X and false otherwise. This is true. The same value. True. Okay.
Yeah.
All right. This line is the same as this line. It's A is substituted with 1, 2. Okay, minimum of A. This is easy, right? What
One.
is 1? Okay. Minimum of this thing. What is this thing?
1 and 2.
Yeah, it's the tuple 1 and 2. Okay.
Okay.
Because there's only one element in this set. Right, this set has this A as only one element. And the only element is the minimum as well as the maximum. Okay. Yeah, let's
Yeah.
try whether this is possible or not. Minimum of 1, 2, 3, 4. 1, 2, 3. What do you think this is?
Uh, I think error.
You think error? No. You can compare, no? Tuple. Minimum 1, 2, 1, 1, 3, 1, 2, 3. What about this one?
Is it
Okay.
error?
Yeah, because 1 compare with 1, okay. But 1 compare with this 1 is not okay. But if I change this to 1, what do you think now? I guess it will go through. My guess, huh? It get through, yes. So you compare 1 with 1 with 1. Okay, everybody is equal. Now you compare 2 with 3 and 2. Okay, so 2 is smaller than 3, but 2 is the same as 2. Then you take the next one. The next one is 3. So you are larger. Okay, so now if we try it with the max, this should get through also. This time I should get the last tuple. Oh sorry, because the 3 already are larger than these 2. So this guy is the correct one. Okay, so we learned something new here. Back to this one. Print C. What is C? C is here, this whole thing. Let's try another guy. Okay, Bruce.
Hello.
Yeah. Okay, C. 1 colon.
C1 colon will be
This is C.
all elements except the zero index element.
Yeah. Next one. C colon minus 1.
C colon will be all elements except the very last element.
This means from the beginning to
To the
before the last,
yes.
excluding the last guy. Okay. So it's 1, 2, 4, 5, A, B. Okay, next one. This one from beginning to the end, you're doing it by step of minus 2. So backward.
Every alternate element backwards. So this will be CA41.
Yeah. This one 1, 3.
This one will be 2 and
Starting from the
4.
second 2 and 4. This one print C8.
Error index
Yeah.
out of bound.
Yeah, this is outbound. Okay, next one. C8 colon.
Empty tuple cause forgiveness.
Yeah. Because of what? Forgiveness.
Use the Python very forgiving.
Oh, okay. Okay. So this one is this kind of trick is used very often in recursion to avoid this kind of problem. So you get an empty list. It's basically it okay lah, you call it forgiving. Okay, fine. Next one, st equal to this. So it's a string A B C D E F. So let's try another guy. Uh, Ray Yang.
Oh,
So Ray Yang.
yeah.
Yeah. So this what is this?
Is it A then backwards F E?
A backward F E. What do you mean?
Then
This is
then
from
then
beginning
continue.
to
Wait.
no, this is from beginning to the end, starting backward. This is the
Oh,
increment.
so
Increment.
A F E D is it the onwards?
No, I think it's FEDB. Let's try.
Oh,
Reverse.
oh,
Right? This is the ending. No restriction on the beginning and ending, but it starts from the back to the front.
oh.
Okay, this one, next one. Oh, now
Uh,
there's a restriction starting from the back and going backward.
so is it E D C B A F?
Starting from the back, so it should be the same, right?
Oh, oh,
Ah,
shoot. Okay.
yeah. Next one.
Uh,
This one starting from the back. No, this is going backward, starting from the beginning.
also like the one I got wrong the first time, is it? Is it the
Uh,
A F?
no, starting
Oh,
from the beginning, you're going backward. So you're starting from the beginning. The beginning it's beginning is A. You're going backward.
so
Backward
A
you got
F E
nothing.
D is it?
No, you only get A.
Oh,
I think you get A. Yeah. Now I'm thinking like the system. So
oh,
this
sorry.
is you start from A and you're trying to go backward. You go backward, you got nothing, what? So it's A only. Next one. You are going backward and you are ending at back.
Oh,
Uh,
this I
you are
don't know.
ending. Let me try. Let me think. So you are going backward. You are ending at the back. So you got nowhere to move. So you should get empty, right? You get empty.
Oh,
Okay. This one, going backward, you are ending at the second last guy. So you get one guy, which is the F.
oh,
This one, you are starting from the very in front, -8, all the way. So you will get same, A, B, C, D, E, F. This one going very in front, you are going backward. You're very in front, you're going backward, you got nothing. Okay, you got nothing. You are going starting from very in front until the end, before the end. So you get everything except F. Right? And this one, last one, you are starting. Where am I now? Am I done? Yeah, I'm done. And this one, error, because there's very in front. Okay, so
Prof, is
this
there
is
resources for all this? Like summarizing the whole.
okay. Okay, so I have already articulated the. It's not a resources, it's an understanding. So you must understand that these three numbers here, one is the starting, one is the ending before, the other one is how you want to do it. Is going forward or backward. Negative means backward. Right? Positive means going forward. So I don't have any positive thing for you to see because it's positive is easy. Right? I always have these negative things for you to see. Uh, Somebody asked me, is line 48 and 50 the same? 48 and 50 the same? Yeah, 48 and 50 are the same. We can go to the first, to the next. 48 is here. we get backward 50. Let's see. No, 50 is not. 50 is starting from the beginning, and then you want to go backward. From beginning, you are A. Going backward, you hit nothing already. That's why you get an A. But 48 and 49 are the same. Why? You are starting from the back, right? The last guy, and you're going backward. Starting from the back, going backward. Therefore, you get the reverse. This one is no restriction, starting from the back to go. So you get everything. All right, I guess the rule that Ray Young is asking is, if you see the back as negative, it means going backward. That's the rule. And then the next thing is that if you don't see any number, you are not restricted. You can use whatever you want. But if you have a number there, it means that you're starting from the back. You're starting from the front. You're starting from -8 and so on. Okay, you try out a few more and then you will see how things are like. That is why I also learn from trying out things to make my thinking sharper and sharper, right? To be able to decipher this kind of stuff. Because I see that, because this is a negative means it's from the back. No, nothing spelled out means no restriction. And if you spell it out, it means you have to start there or you have to end there for the second number. Okay, that is the recipe. Question 3. Okay, question 2, nothing interesting. Question 2 is just knowing that the how to print out 1, 2, 3. So simply just put, if you put 1, 2, 3, you will print out 1, 2, 3. How to print out this guy? But this guy is tricky, right? Because there's a parenthesis and you cannot print this out. So if you try to do it, you get back the same thing. So this is nothing that you can do about. You have to put a string. String. That means you put a code there. All right, you get this. How about this one? Oh, this one is possible because there is this is a proper thing. So you can have it with 1 and then 2 and then 3. Okay, or you can also have 1 and 2 plus a 3. You get it. Or you can have 1 plus a 2. Or in this case, I need a tuple 2 and a tuple. So I have to have this. Okay, plus 3. Yeah, right. Yeah. All right, many things, many ways to write this thing. What about this one? This is easier, right? So this is simply 1, 2, comma, plus 3, 4, comma, plus 5, 6, comma. Of course, if you forget about the comma, then you are in trouble because this one means nothing. 5, 6 is not a tuple anymore. It's you will get this. All right. So question number 2, nothing exciting. Question number 3. Okay, question number 3 is write expression to that will return the value 4 when the x is bounded to the following values. This is also quite straightforward. So when you use Python tutor, you can see that this tuple, this 4 here is 0, 1, 2, 3. So this is a tuple at third position. This one is 0, this is first position. Inside there is a tuple, so it's index of 1, then followed by index of 2. So you have index of 1 followed by index of 2. The last one is index of 1 to give you this thing, and then index of sorry, index of 1 to give you this thing, and then index of 0 to give you the middle one, and then another one, 0. So you have 1, 0, 2, 0. Okay, let's see. Okay. So you have the S is this thing, S3 is what we want, so the third guy. So it's 4. The length of S is 7. Is T is this guy, this second guy. It looks like this. And T1, 2, so T1 and 2 is 4. And the length of T is 4. The length of T1 is this guy is 3. Length of T2 is T2 is this guy is 2. The length of T3 is an error because this is a number. There's no length to it. All right. So and then this is last guy, last one. You want the 1, 0, 2, 0. So this is 1. Sorry, this is 1, 0, 2, and a 0. We get the 4. The length of U it's just this 3. The length of U1 is this 1, that is 2. Length of U1, 0, 1, 0, which is this guy, 4. The length of U1, 0, 2, 1, 0, 2, which is this guy is 1. And the last one is an error. Okay, you can see the error. Because this is simply a number, so it's an error. Okay, object of type integer has no length. Okay, that's all for question 3. Question 4, it's as I emphasized that just now, this is not a question suitable for tuple, but since you are asked to do it in tuple, so we do it in tuple. All right, this one allows us to understand a little bit about the tuple operation. So, okay, so all these things are here. And I've created 3 courses, 10X, MA1001, and MA something. And in NUS, all these are digits to indicate different things. The first number is the number of hours for lecture. Second number is the number of tutorial hours. The third is the laboratory hours. The fourth is the estimated homework hour. The last is the preparation work that you have to do. In NUS, all the modules are, for example, 4 MCs. Each MC requires you to do work for 2.5 hours per week. So 4 MCs class means that you have to do 10 hours of work per week. And therefore, usually students take 5, each student takes 5 units, 5 courses for 50 hours of work. The normal working hour is actually 40 hours. But as a youngster like yourself, you can do a little bit more. And so this added up, it's 12. So this is 12 units. 12 units is about divided by 12 hours is divided by 2.5, so it's about 5 modular credit. All right, anyhow, that's the background why this is there. So the modular total unit is the unit of this. So in this case, this is the design of the system with a module is made up of 2 parts. It's a course code and the units of the thing. So this is so-called the derived data structure. Instead of just simply tuple, so I could have I need not have this thing, the design. In this case, the design it's the course is a course code and then followed by a unit. it could be designed differently. For example, it could have been, uh, for example, like instead of this, you can say, oh, instead of this, you could have said this is the, basically take the whole thing here and dump it here. This will be an alternative. This alternative is not as clean because this is the course code. And then followed by hour. Instead of that, all these hour can be lumped into just simply the units. And this unit itself is yet another tuple. So this is a tuple of tuple. So this is a particular design. You can dispute it. You can, for example, dispute it by, hey, actually this is better with a list. Okay. But tuple is used here. All right. So this is just a design. So there are different design for different purposes. So now we are seeing this. So the first thing we needed to do is to make empty schedule. So these are the courses. So let's run it until here and see how. All right, so these are the basic, and then now I create a class. All right, this is a class. Oh, not yet. I need to create the units. To create a class, I need to create a unit. Then now I have a class. Okay, so this is a class. So this is a design with a tuple and a tuple for this course. Same for the other one. All right, same for. So now I have three courses. This course, this course, this course. So the question asks, part A. Make empty schedule. So how do I do that? This is a straightforward. Make empty schedule. So this is straightforward. I will just simply return an empty set. Okay, or empty tuple. Sorry. So how much time is this? This is nothing, but I don't use any. It's constant. So 1, and the space is also constant, which is 1. Okay. The second part is to add a class. Basically, I want to make a schedule for myself, and then here make a schedule. Then I want to add class, add class, add class. So I'm adding these 3 classes to myself. So how do I add class? So can I see your work in the chat box? So let's see what you have. Okay. Return schedule plus this. Okay. Get module. Any more? Okay. 单元数. There's something wrong there. Okay. Leon, you forgot a comma. Not to forget a comma. Someone do yeah. Okay. So Leon, you see, you're missing a comma in your course. Okay. So roughly that is what you should know. Let me cut and paste. All right. So most of you would have done this at a course by return schedule plus the course. The course is you have to make it into a, so schedule is a couple of tuples. So this you have to make a course into the schedule. So it should be like this. All right. So if you do this, how much time and space? Let's yeah, 财资源 Hi, Ziyuan here.
Yeah, hi, Prof.
Hi.
The time should be both is on.
Both is what both? Oh, I mean time
Both,
and space.
yeah, both time and space is on.
Oh, why?
Because when you output schedule plus cost, it only stores like the it only stores it only stores the n. Sorry, is it n square?
No, it's n. Yes, you
Or
are right.
is n? So
Yeah.
so when you output schedule plus cost, it's just like the thing itself.
It's not the thing itself. This is a schedule coming from here, but schedule plus something, it's a new tuple. You are copying everything in here into this whole thing is a new thing. So the number of courses in the schedule is added with 1. So n is, so this is linear. And the space is linear. The space come from here, the two things added together, where n is the number of courses in schedule in the input schedule plus 1. Okay? Can?
Yeah, can, Prof.
Okay. Now, if we want to be more careful, in case the cost is already in there, we don't want to add it. So maybe we should change this to if cost in schedule, then return schedule. Okay. Else return schedule plus this. So this one is a little bit of checking to make sure that you don't have duplicate costs inside your schedule. If we do that, would that change the time complexity and space complexity? 财资源
If I this the time will be n squared, but the space is still on.
Why the time is n square now?
Be- because because of the if cost in uh it because sorry, is it is it all cost and OMN, like
Okay, how do you check whether a course is in a schedule? If you follow
wait. So
this,
sorry, it is n squared. Sorry.
huh?
Eh,
No, you're wrong.
oh,
Yeah. So let's see. We go to tuple. Do we have tuple? In membership, ON. Okay, linear search. Space O1. Okay, why? So it means that when I need to, when I do cost in this, how do I do it? The system will check cost one by one, right? To ascertain, right? Whether cost is in the schedule. Okay, so if you're doing that one by one, how much time? Check the first cost, check the second cost, check the third cost. So this will be O and time to look through and causes in schedule. Okay, so this is O of n. Come, I cannot move my. Yeah, we are writing too long. Okay. Right. So this is O of n, and we examined just now. This is also O of n. So O of n to check and return this to create this new list. This is no create. It's actually reusing the old schedule, and it doesn't create any new space, right? In this case, but this one does. So we still have O of n and O of n for the time and space. Chai Ziyuan, are you okay?
Yeah, Prof. Just checking, is it actually the same as OMN? Like basically, it's actually never mind.
No. You have to say you can ask your question. Okay, let me give you the second version. Then you have your then maybe that help a little bit. So the second version it's for fun only. The second version is to use recursion. So in the past exams or assessment, usually you are given iterate recursion. It's iterative. You are supposed to ask to write a recursion. And today in the forum, I posted for you to actually write me can you write me an iterative version? Okay, so if you ask the same question and so now we have this as actually iterative version, correct? Chai Ziyuan. If we want to write a version that is recursive, how will we do that? And can you guys try it and post it in the chat box? All right, this is iterative, right? Many of you would have written this. What happens if we write for fun? I don't mean that it's better, but let's see. A recursive version. But that should be the spirit from you also. Whenever we ask something, actually you should vary, change the question somehow and try to answer it yourself. This is where how we also create our exam questions. Okay, by trying it out ourselves. Anyone? I don't see any recursive one. So because this one is I have to check, right? If the schedule is in the course, then if it is already in there, I get it done. But if I don't do this checking with the in, I have to write it myself. I see it now. Wang Yuanqing. If not schedule, return. I see if it's empty. Then you're missing some checking. You still have to check. You're not checking at all. Okay, so here it's how it should look like. Yanqing, you have one less checking. You lost the checking.
The
So
course in schedule.
yeah, it's here. So you check this, Yanqing, you did this. Okay, but you forget to check this. Okay, you need to check whether the course is in the schedule or not. If it's already in the schedule, you just return the schedule, which is the same as this guy. So this in is now being translated into checking the first guy with it. And because of the recursion, you will be checking one after another. All right, so this statement of searching in the course in the schedule or not is now translated into a simple checking of the course in the first schedule or not, in the first course in the schedule or not. All right, if it is, then you return the schedule. Otherwise, you return the course. This course is you have to keep it and you have to do this recursively. So now, Wang Yuanqing, how much time and space is this?
See.
Let's try. See, this is a good exercise. It's the ridiculous thing to do, but it's good to see it. You know.
I'm not really sure, but I think it's n square.
Mm-hmm. Yeah, you're not wrong. You're correct, actually. Why is it n square? You try?
Because
You
with
want
each recursion, like you create a new tuple.
to?
So it's like 1 plus 2 plus until n. So it's n
Mm.
square.
Okay, this is how, there's one way to see this. Let me write it down here. Okay, so the time that we want to know is that where n is the number of pauses in schedule. Okay? I don't like this. Oh, okay. So the total time you need for n, which is the size of the number of pauses in the schedule, is equal to what? How much time does this take? This take over 1, right? Just to check, right? How much time does this take? This is also over 1 only, right? If it happen here, then you're done already. How much time does this take? This is also over 1, right? And you return this is you just return, so it's over 1 also. So the cost come from this statement then. Okay. So how much time is this statement? This statement is O of 1 to take this guy out plus how much time is this? This time it's this guy is the recursion and this is the same as the input. This is 1 less. So this is by right, this is t to the n minus 1. Okay? Because this is the same function as this. So since we use Tn, we have to have, in this case, the size is n minus 1. So you pay for it. More than this, that you actually also pay for making this new tuple. Correct? This is a new tuple. You know that tuple is immutable. And you have this schedule. If you take one less schedule, you're copying, making this from here. So this is you're paying for n minus 1 also to create this, and then you call this function to pay for this. So in total, what do you have? You have O of 1 plus, you do this checking, and then you do this checking plus O of 1. Actually, I could have ignored it. Plus this O of 1, all right, plus this O of n minus 1 plus t n minus 1. Okay, so this is a first layer that you get through. Of course, you can simplify this into O of 1 plus O of n minus 1 plus t n minus 1. Okay, this 3 O of 1 is simply a O of 1. This one is copy here, this one is copy here. Now, this is the trick about telescoping. This is called telescoping because it's O of 1 plus O of n minus 1 plus this. You don't know what is this, right? But you know that it's Tn. So just put n minus 1 into him. So you will get O of 1 plus O of n minus 1 become n minus 2. N minus 1 minus 1. So it's n minus 2 plus t. And this n minus 1 become n minus 1 minus 1, n minus 2. Okay. And then you now see the pattern. This is simply O of 1 plus O of n minus 1 plus this O of 1 and this O of 1, you don't lose much. You will just lump them into here. If you continue doing this, you will know that this become O of n minus 3 plus O of n minus 4 plus until all the n to t to the 0. or t to the 1, okay, which is O of 1, which is n minus n plus 1. All right, now you know this is n plus n minus 1 plus n minus 2 plus n minus 3, n minus 4 until 1. So this is Tn. It's equal to O of n squared. Okay? Wang Yanqing.
Yes.
Okay. So you also notice that I didn't say this is time or space, but actually this is both time and space, because copying here, it's this space is also accumulated from n minus 1 to n minus 2 to n minus 3 and so on. So both the time and the space are n squared. All right. Okay, so now I have done part B. What is part C? Total schedule units. Given the schedule, how to do this? Oh, this is simply adding up all the numbers, right? All the number in each case. So this cost is 1010X is how many? 12. And this one is 10. MA11024610. And this one is 247. So if I have print it out, I should get 29. So I have to work this out. So how do I do this? This is simple. So just give it to you. I break it into two routines. So first I get the unit. I reuse some of the code. So then total is 0. For each course, I will go through it and then I print out. So let me just print out and see how. Here, I should get 10 plus 12 plus 7, 29. Oh, I should let it go. 29. Okay, and this become very messy now. Okay, we are not done. We have to check how much time and space is this guy. Let's see. Alger. Alger.
Yes, hello.
Hi. So what do you think? What's the times and space here?
Um,
So one by one, how much time is space? How much time and space is this guy?
O and
Huh?
O, time is O1.
Oh, one. Yeah, because there are only 5 components, right?
Mm.
1, 2, 3, 4, 5 components to add together. So there is O1. Space?
Space O1.
Yeah. Space can never be larger than time, huh? So we always remember that. Okay, next one. This one.
And this is ON.
O1 here. And this one is
Iteration.
huh? O
Next
what?
one.
Huh?
I thought this was iteration on master.
Sorry?
No, it's okay.
Okay. What is it? What is it for cost in schedule?
I thought this was iteration. Yeah.
Yeah, this is the iteration.
Oh, okay.
This is the iteration. For each course in the schedule, I do some finding out the units and then I add it to the total. So this is what?
ON.
ON, where N is
N is the number of courses.
okay. Okay. And that's it. So this is ON. And What about space?
1.
Huh?
Space is O1.
Oh, one. Okay. Now, next one. D, drop class. This should be easy for you now. So can I see something in the chat box? All right, can you post something in the chat box and then let's take a look? Okay. Yeah. Okay. So yeah, once you know how to add, you should know how to drop. Okay. So the same thing for the drop. All right. If the cost not in the schedule, there's nothing to drop. Return the schedule. Otherwise, you find out where is the cost in this index. You just slice it until there, excluding him, and uh, skip it and to the end. So this is the cost. So you know that this is also ON, where N is the number of courses in there. And this is also searching for the index. And if you are not sure, you can always check the index. It's O of N for the time. And the space is O of 1 is linear search. Okay, so this is also O of N for the time and O of 1 for the space. And what about this? This is slicing, dropping one of the items and the space you require and the times you require. It's both O of N. Okay. So the time is O of N. The space is O of N. All right. So this is the straightforward version as we normally should have. We can be funny by doing another version as before, doing the recursive version. And you should guess that the recursive version is also the n squared time complexity. All right, so it's here. All right, so the drop the class, the schedule is empty, you return the schedule. If the schedule is the same as that course, then you drop that class. Oh, drop that class from here to you drop that class. Actually, you can just simply do it with assuming there's no duplicate, then we should be able to just return this. If there's duplicate, then you cannot. But if no duplicate, if the first class is the same as the course that you want to drop, you just return the rest of the schedule. So that should work. Assuming duplicate. Okay. Otherwise, you have to keep the first course and recursively drop the class. And you ended up with the same thing as before. Right, O of 1, 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 creating this, it's O of N or N minus 1, make no difference. Then you have to recursively doing this. Okay, maybe I have extra O of N here. All right, so the recursion looks like this, and this is what I meant by telescoping. Okay. All right, so this is n squared, no doubt. The space is also n square because you're stacking up this plus thing and you are creating copies of this. If you like, you can see it, but it will be very messy here that things get stacked up one after another. Okay, that is D. Okay, what about next one? E. Implement the credit limit. So you are not supposed to take so many classes. There is a maximum credit that you can have. If you have more than that, you have to drop the class. So can I see some posting of your solution? Okay. E. Yeah. Oh, I see. So the first solution I'm seeing is that you just taking the schedule until you max out the credit. Okay, that's fine. Okay, any more? All right, so you're recursively doing this thing until you have not exceeded the credit limit. Okay, let me just give it to you. All right, credit limit, schedule maximum credit. Total is you first find out your total. While your total is larger than the maximum allowed, you take one schedule off your schedule and you reset your schedule to be this with the one drop off, and you recursively doing this until you don't exceed the maximum credit. So how much time and space? All right, you see that this one is easy. This one is total credit. This is O of n, where n is the number of courses in there. And then this is O of 1 for how many times? For at most O(n) time. Okay. And you subtract this schedule. This is also O of 1. And you drop this. Oh, this is tricky now because you're dropping, right? So you are paying for the space to create a new schedule. It's your new schedule. And you also pay O of n minus 1, O of 1 time to copy the schedule over. So this thing going around from O of n, n minus 1, n minus 2, and so on. So this is going to, in the worst case, this is going to be O of n squared. And what about the space? Now, that is an interesting one. So let's try. Sun Si Yuan. What do you think the space is?
No problem.
Yeah.
Space. Is it constant?
No, it can't be constant already. The space here is already used up. O of n already. You are creating a new. This is not in the input anymore. The input comes in, we change to here. All right, this input come in, you're creating a new tuple.
Is it n? I think it's n.
Why is it n?
Every time you create a new schedule, the old schedule will be discarded.
Yeah, that's correct. So you're reusing the because we reuse the schedule. Okay, so it doesn't accumulate. Unlike the case of this recursion, it just stack onto each other, so they become n squared. All right, here it doesn't. Here, space, the last round to the next round, the space is overwritten and the garbage is being collected and not counted anymore. So the footprint that we are seeing here is O of n only. You're right, okay? Now, the last question implement an improved version of this. So can I see what you do? So basically, you want to max out your credit limit, and yet you want to take as many courses as you can. So as you know, there are different sizes of some of it with a lot of credit. There are some with lesser credit, but it's still good. One course, one course, one course. So you want to take as many courses as you want while still not. So okay, so I'm seeing sorted the sorting of the schedule from the lowest credit to the from small to larger, and then drop from largest to smaller, I guess. Or from the so smallest to largest from Bruce, and then he drops the last guy, which is the largest in credit. Okay. I also see Tan Yuan Su. Okay, so you have two strategies. One is that you continue adding. The second one is you just keep collecting one after another. The other one is you keep dropping until you have not exceeded the credit limit. So here's one example that you should see. So for example, your credit it's for one course is 10, another course is 10, another course is 10, 11 and 12, 12. So if your credit limit is 41, say, then the solution could be 10, 10, 10, 11 for four courses with 41 unit. On the other hand, if you get the last If you get the last from the back, you will get 12, 12, 11. You cannot add anymore. So you have already 35 credit. If you take another course, 10, you will get 45, exceeded the credit limit. So this is the solution that you're looking for. With credit limit of 41, you can take four courses of 10, 10, 10, 11. Okay. So the the way to do this is the plan is that either you take courses one by one with the smallest in unit come first until you hit the credit limit that you can't take anymore. That's one way. The second way is that you take all the courses and start dropping one by one until start dropping one by one, start dropping one by one with the largest unit come first. Okay, until you no longer no longer exceeded the credit limit. Okay, so these are the two strategies you can have. So I give you one. My one is that I don't do sorting. So among between these two, you also have two strategy. One is with sorting, and the other is without sorting. So with sorting, it's you one-time effort, and usually when you do that, you pay upfront. You're paying upfront with O of n log n. Okay, upfront you pay already. The other one without sorting is that each time you pay O of n to look for the largest or smaller, depending on which strategy you take. Okay, so here I have I prefer not to do sorting. So what do I get? I do this. I replace this part with my new while loop. My new while loop while my total is greater than maximum credit, I find my largest zero index zero first. Then I go through a loop to find who is the one that I need to remove. Then I remove him and I get a new schedule. The new schedule is from the beginning to the one that I need to remove before that. And then the one after I need to remove to the end. So this is my strategy. I do not use the sorting, but I find the largest to drop, and I keep work on it by dropping from the largest until I have enough. Is that okay? So this is just many ways of doing the same thing. I choose not to do sorting. Usually sorting it's a price that you pay upfront if you need to, but I could be lucky if I do this. Maybe I drop one, it's more than enough. I can finish my work and my time complexity will then be ON. But if I'm lucky. Okay, then maybe I should write it here. If I am lucky, I may get away with ON for the solution. Okay, because I only need to drop one or two courses. If I am unlucky, I need to drop order of n courses and I will then pay for O of n squared still. Okay. All right. On the other hand, your case of sorting will pay upfront O of n log n. Of course, there's other costs there that in this case, you also do this. You also do this creation of this each loop. You actually also pay ON. So you are also not running away from ON square. But more than that, you are also paying for the ON log n for the sorting. All right. And ultimately, both are still ON square and ON space. ON square for the time and ON for the space. Okay, I'm done with this recitation until here. One thing I needed to say about this is that actually this is how can you be sure this is correct? So I utter so many strategy for you, but you should question me why I can be sure this is correct. And this is actually proof of correctness. And I will try to do this for you next week. Okay. Proof of correctness is grounded with mathematics. We still have to argue why this is a looping. A looping achieves some kind of invariance, and that invariance allow us to argue that the whole thing after finishing, you get a correct answer. All right, so that's what I said just now. For some of you who are not here, but this is actually what I say in the review. All right, you learn about writing the code, anyhow to write the code, and then you write good code, and by making comments and use variable names meaningfully, and you write efficient code, and then because you understand time and space complexity, the one more step that you have yet to learn is the correct code, meaning that you need to prove. Of course, like here, gut feeling tells you that you are correct, but the gut feeling is still gut feelings. All right, you have to be grounded with mathematics to prove that this is indeed correct. For this case, it's easy to prove actually. And in some other cases, we may not be that lucky to be able to prove it. So here also stated that proving is not a training in this course. So we will be very gentle with you to require you to understand proof. Okay, great. I finished in time. Any question? Yes. Lin Che. Yes. What is the question?
Hello, Prof. My
Yeah.
question to you is why you don't want to use list to do the schedule?
No. Not that I don't want to do. I'm saying that the question asks you to use tuple.
Is it? I did
Yeah,
everything in list though. Yeah.
because this recitation is they never say anything about tuple list. It's all tuple.
Oh, okay.
Okay. Recitation 5 should be list then.
Okay.
Okay. Yeah, yeah. You can do it with list. That's fine. But you may have less learning point for the, you will see some of this stuff as n square no longer there. Correct. I did that for one of the reviews. I show you the various way of doing the recursion, and they are at time if you are list, you can get away with n square.
Yes. Okay.
Okay.
Thank you.
Thank you. Any more? If not, then we call it a day. Oh yes, there's a question here. Okay, there's a question of part F. Are you talking about this one? The part F is this one, the credit limit. Okay. So you see, just take my solution to examine this. So uh, to know that this is n square, how do I know? So this one is this checking is O1, right? So nothing. But how many times I have to check? Potentially, I have to drop maybe half the number of causes. So this is O of n divided by 2, okay? Or then we just simply use On, okay? So potentially, I may have to drop On causes in the schedule, okay? And then, so this loop potentially On times. Then this one is O1, nothing. This one is O1, nothing. This one, for I in schedule, get the total unit. So how many times is this? This is O of n times time. And this is O of 1. Okay. This is O of 1. Okay. And this one also O of 1. Nothing exciting here. This one also O of 1. This one also O of 1. This is a tricky one, right? So this one is creating a new schedule from the old schedule by dropping the guy and the index there. So this is O of n time, correct? And this O of n times will become O of n minus 1 time in the next round, next iteration of the while loop, okay? In the next while loop, then O of n minus 2 time in the next while loop, and so on. So the total by the while loop is then O of n plus O of n minus 1 plus O of n minus 2 dot. I'm ignoring all the O of 1, okay? You don't need to care. If you want, you can also put it in O of 1 plus that, and then O of 1 plus that, and so on. Ultimately, this O of 1 or sum up at most O of n. The more important one are the O of n, O of n minus 1, O of n minus 2. And that turned out to be O of n squared, as you should have learned by now. Is that okay? Okay. Any more? All right. If no, then let's call it a day. All right. The question to be done is here. Review number 7. This is interesting. This one actually was provided by your TA. Okay, bye-bye. Give me a check and go. Let's go. Okay, thank you.